Hey guys, Raph here for Simpson Math. I know this is kind of a new video because I'm not Mr. Simpson. Look at that, I'm obviously very brown compared to him. But yeah, let's get into it. So first we can do a little observation. As you can recall, earlier in the semester we did a golden-cheeked warbler problem, focusing on a graph that looks similar to this. And basically, that problem described how population growth occurred in a population. So first, obviously, it increases rapidly. And then as resources become more and more limited, it still increases, but at a slower rate, as shown. So what this causes in the graph is a change in concavity. With at first there's a concave up part of the graph right there at the beginning, and then a concave down part of the graph. And then in the middle, where the concavity changes, there is a point called the inflection point. Right in between. So here's the actual definition, formal definition given to us. An inflection point is the point x, comma, f of x, so of the original function on the graph of a function where the function changes concavity. Emphasis on changes. It has to change concavity. Alright, so next, we're going to do an example problem. We're going to find the inflection points on the curve y equals x times e to the power of negative 2x. So to find the inflection point, we have to look at the behavior of the second derivative of this function. So first we have to find the first derivative. We can use the product rule, so x times negative 2 times e to the power of negative 2x. And I found the derivative of e to the power of negative 2x by using the placenta rule, so just bring the negative 2 forward, or to the front. And we can add that to e to the power of negative 2x times 1. And we can simplify this by factoring out a e to the power of negative 2x. So then you're left with negative 2x plus 1. And then again, you can do the product rule to find the second derivative. So negative 2 times e power of negative 2x times negative 2x plus 1 plus e to the power of negative 2x times the derivative of this, which is negative 2. So now we can factor out negative 2e to the power of negative 2x, because they're on in both terms. So then we have negative 2x plus 1 minus 2, or plus 1. This should be plus 1. So then if we simplify all that, it should be negative 2 times e to the power of negative 2x times negative 2x plus 2. So it's supposed to be 1 plus 1. Okay, to find the inflection point, you have to know when this value is equal to 0. So when the second derivative of your function is equal to 0. Well, we know that e to the power of negative 2 times x is always going to yield a positive value. So we have to look at this part. When does negative 2x plus 2 equal 0? Because if this equals 0, then the whole thing will equal 0. Well, you can do algebra, or you can just do it mathematically in your head. And it turns out that our x value will equal 1. Now we can do some analysis over this inflection point. You can say that we can draw out a number line of which represents our domain. So 1, we have 2 here, and we can have 0 here. This would be our inflection point. And then we can look at the behavior of whatever happens at the 0, because that would describe the behavior of the graph on the left side of this inflection point. So we can plug in 0 to into the function, into the derivative, and that's into the second derivative. E times -2 times 0 times -2 times 0 plus 2. So we're left with a negative value times a positive value times 0 plus 2 would be a positive value. So that means our behavior on this left side would be negative. Now we can do the same for this right side. Plug it into our derivative equation. Times 2. -2 times 2 plus 2. And then we can say that we have a negative value times a positive value times a, so you have -4 plus 2, another negative value. So and then the behavior on the right side would be positive. Now what this means, the derivative, if the second derivative is positive on the right side, that means that the original function y will have the behavior of a concave up. The intervals in which it is concave up is from 1 to infinity. Now we can say the same thing about the left side of the graph before the inflection point, where it is concave down because the second derivative is negative on that side. From negative infinity to 1. Now, as you remember, it asks us to find the actual inflection points of the curve. So we have our x value, which is 1. So all we have to do is plug that into our original problem, our original function. Times e to the power of -2x. So y is equal to 1 times e to the power of -2 times 1. So and then your y is equal to e to the power of -2. So then your point would really be x is 1, and then your y would be e to the power of -2, and then that's your inflection point. What am I supposed to say at the end? Great. Math made simple with Simpson Math. Thank you for watching. Make sure you guys like, subscribe, comment, all the above. Thank you.